Vortex bladeless. The vortex bladeless is the only wind generator that produces no rotation, harvesting energy from a cylinder that does nothing but shake in the wind. As air flows past its vertical mast, it sheds alternating swirls of low pressure in a pattern called a von Karman vortex street. And when the frequency of that shedding matches the natural resonance of the structure, the mast oscillates and an alternator at the base converts the wobble into electricity. The smallest model, the Vortex Nano, stands about 3 feet tall and produces 3 watts, enough to trickle charge a battery for an off-grid sensor. The Vortex Tacoma reaches about 9 feet and produces 100 watts, and a residential version, the Atlantis, is designed to stand between 30 and 43 feet and target 1 kilowatt. Because the design contains no gears, bearings, shafts, or spinning blades, there are no contact surfaces to wear out and no lubricants to replace, which drops maintenance, the largest recurring cost in small-scale wind power, close to zero. The trade-off is that a vibrating cylinder extracts far less energy per unit of frontal area than a spinning rotor, so the Vortex competes on operating cost and silence rather than raw output. Altairos Buoyant Airborne Turbine. The Altairos Buoyant Airborne Turbine is a wind turbine that flies, lifting a conventional 3-blade rotor inside a helium-filled fabric ring to 1,970 feet, 4 to 5 times the height of a standard turbine. The winds at that altitude carry 5 to 8 times the power density of the air near the ground, letting the BAT generate more than twice the energy of an equivalent tower-mounted machine. The toroidal shell does 2 jobs at once, holding the structure aloft on helium buoyancy while its shape generates aerodynamic lift as the wind passes over it, keeping it stable in the gusty shear layers up high. High-strength tethers anchor it, and a single conductive tether carries electricity down to a ground station that ships inside 2 standard containers and can be generating power within 24 hours of arriving on site. That portability was the business case. The BAT was built as power in a box for remote diesel-dependent sites, mining camps, islands, and military posts where fuel trucking can push electricity above $1 per kilowatt-hour. Altairos stopped developing the platform in late 2015 and redirected the aerostat technology toward telecommunications, defeated by the cost of helium logistics and the difficulty of clearing civilian airspace. Quiet Revolution QR5. The Quiet Revolution QR5 is a vertical axis turbine built for the one place conventional turbines fail outright, the roof of a building in a dense city. It stands about 16 feet tall and 10 feet in diameter, weighs around 990 pounds, and carries 3 blades twisted into a helix of carbon fiber. A straight-bladed vertical turbine slams through a torque pulse once per rotation, generating noise and hammering the blade roots with cyclic stress. Winding the blade into a helix keeps some portion of it at a productive angle to the wind, no matter where the rotor is in its turn, which smooths the torque into a steady pull and removes the vibration. Because it is omnidirectional, it captures the swirling, direction-changing wind that tumbles over urban rooftops without turning to face it. The QR5 is rated at 10 kilowatts in a wind of around 25 miles per hour, and a permanent magnet generator built into the base eliminates the gearbox. A bank of 10 units on the Discovery Tower was projected to produce 77 megawatt-hours a year. Darius turbines cannot start themselves from a standstill, so the QR5 runs its own generator briefly as a motor to spin up before the wind takes over. Makani Energy Kite. The Makani M600 generated electricity not from a tower but from a tethered aircraft flying loops in the sky, a carbon fiber wing the size of a small airliner held aloft on a cable nearly half a mile long. The wing spanned about 85 feet and carried 8 rotors. On the ground, the rotors worked as propellers, lifting the wing off its perch like a drone, and once it climbed to around 1,000 feet and began gliding in tight vertical circles, they reversed their job. The 8 of them combining to drive generators rated at 600 kilowatts, enough to supply about 300 homes. By replacing a steel tower and a massive rotor with a wing and a cable, the team, which began at Alphabet's X Lab, built a machine roughly 90% lighter than a conventional turbine of the same rating. Opening deep water sites where a fixed foundation is impossible. In 2019, they flew the kite offshore from a buoy off the coast of Norway in partnership with Shell. Alphabet shut the project down in early 2020, concluding the path to a profitable product was longer and riskier than the engineering progress alone could justify. The Saphonian. The Saphonian replaces the spinning rotor with a sail, a bladeless converter shaped like a shallow dish mounted on a mast, modeled on the rigging of ancient Carthaginian ships. Rather than turning, the sail traces a back-and-forth figure-8 path, and that motion drives pistons that pressurize hydraulic fluid, which can either spin a generator or feed an accumulator for later, giving the design a built-in path to energy storage that a direct-drive turbine lacks. The Tunisian company behind it, founded by inventor Anis Awini, removed the three components that cost the most and fail the most in a conventional turbine: the blades, the hub, and the gearbox, which it says makes the machine around 45% cheaper to build. With no swept blade arc, it poses no hazard to birds and runs quietly enough for populated areas. The company claims its second-generation prototype captured more than twice the energy of a bladed turbine of the same swept area, and even claims to push past the BET's limit, the physical ceiling that caps any conventional rotor at 59% of the wind's energy. Those are vendor claims. Independent testing has not confirmed, and the BET's claim is physically contested. So the Symphonian remains a prototype rather than a deployed product. Chal Energy, Magnus Vought. The Chal Energy Magnus is the only wind turbine designed to keep generating power inside a typhoon rather than shut down and survive one. In place of airfoil blades, it carries vertical spinning cylinders, and when wind crosses a rotating cylinder, it produces a sideways lift through the Magnus effect, the same force that bends a curveball or a struck soccer ball off its path. Small electric motors spin the cylinders, and adjusting that spin controls exactly how much force the wind generates, so the turbine throttles itself in a gust instead of running away and tearing apart. A conventional propeller turbine has to cut out around 56 miles per hour, but the 10-kilowatt Chal Energy unit keeps working far past that. The rotating head weighs about 24,000 pounds, sits on a steel tower of around 12,000 pounds, and the whole structure reaches 50 to 65 feet. The demonstration site in Batanes in the Philippines is rated for winds reaching about 211 miles per hour, and during Typhoon Hagupit in 2020, the prototype on Ishigaki Island in Japan generated electricity in gusts measured at around 68 miles per hour. At 80 feet in an 18-mile-per-hour wind, it registers 52 decibels, the level of a household air conditioner. The cost is the electricity those motors consume, a parasitic draw that pulls down the net efficiency, a clean aerodynamic test would suggest. Tire wind. The tire wind turbine generates electricity without turning a rotor, flapping a pair of wings the way a hovering hummingbird does. Each carbon fiber wing measures about 5.25 feet, and the two together sweep roughly 11.7 square feet. Rather than converting the wind into the circular motion of a propeller, the Tunisian designers built a mechanical converter that translates the reciprocating figure-8 path of the wings into rotation at the hub, drawing power on both the upstroke and the downstroke. The pilot machine tested in Tunisia is rated at 1 kilowatt, a deliberately small proof of concept. A wing tracing a tight figure-8 presents a far smaller and slower-moving profile than a blade tip cutting a wide circle at high speed, which lowers the noise signature and reduces the risk of bird strikes, and the compact motion lets units sit closer together in a wind farm without one stealing air from the next. The weakness sits at the joints. Every flap reverses the load on the mechanical linkages, and reciprocating motion fatigues connection points faster than smooth rotation does, the central durability problem the design has to solve before it scales. Ming Yang Mi SE 16 242. The Ming Yang Mi SE 16242 is one of the largest offshore wind turbines ever certified, rated at 16 megawatts, with a rotor about 794 feet across. Its swept area covers the footprint of more than 6 professional soccer fields, and its hybrid carbon fiber blades each run about 387 feet, longer than a football field, including both end zones. Rather than a full gearbox or a pure direct drive generator, Ming Yang pairs a compact medium-speed gearbox with a permanent magnet generator, holding the weight at the top of the tower below, 41 tons per megawatt. That low head mass reduces the bending load running down into the tower and foundation, letting the supporting monopile or jacket be built lighter and installed cheaper. The company projects that a single machine, operating under design conditions off the Chinese coast, generates about 80 million kilowatt-hours a year, enough to supply more than 20,000 households, and over a 25-year life displaces roughly 1.8 million tons of carbon dioxide, compared with coal. The platform is rated for typhoon-class conditions, the requirement that drove its development because the South China Sea destroys turbines built to calmer European standards. Windspire. The Windspire is a vertical axis turbine shaped like a narrow column, built to stand beside a house or office rather than on a remote ridge. It rises about 30 feet on a slim tower, and its rotor is a tall, narrow cage of straight vertical blades that catches wind from any direction without turning to meet it. Rated at 1.2 kilowatts, it feeds a low-speed permanent magnet generator that puts out single-phase alternating current at 120 volts, the standard household supply in the United States, letting it connect as what the maker calls an energy appliance rather than industrial equipment. By eliminating the wide swept circle of a propeller and the tall lattice tower that usually supports one, the wind spire occupies a footprint small enough to sit near occupied buildings and runs quietly enough not to disturb them. The cost of that slim profile is efficiency. A narrow vertical rotor captures far less energy than a horizontal propeller of comparable height, and the straight blades load and unload once every rotation, subjecting the structure to the cyclic fatigue that limits the working life of every straight-bladed vertical axis design. Wind tree. The wind tree is a wind turbine disguised as a tree, a steel structure about 36 feet tall and 26 feet wide, carrying 72 small vertical axis turbines shaped like leaves, each one called an aeroleaf. No single leaf produces much, and the whole tree is rated at around 3.1 kilowatts, roughly the output of a small home solar array. What it trades away in raw power, it makes up in where it can stand. The leaves begin turning in winds as light as 4 miles per hour, well below the 8 to 10 a full-size turbine needs to start, letting a wind tree generate on roughly 280 days a year in an urban setting where the wind is weak but constant. Each leaf is a direct drive unit with no gears or belts, so the structure runs in near silence and presents no large spinning blade to strike a bird. The French company behind it built the machine as much for the look as the output, placing the trees in plazas and along streets where a standard turbine would be rejected on site, accepting low efficiency as the price of putting wind generation in the middle of a city. Invelox. The Invelox does not put its turbine in the wind at all. It captures the wind in a large funnel, mounted up high, then channels it down through a tapering tube to a turbine housed at ground level. As the passage narrows, the trapped air is forced to speed up through the Venturi effect, the same principle that makes water shoot faster from a pinched hose. So, the turbine meets a wind stronger than the one blowing outside. The company that developed it, Shearwind, reported in testing that the system could roughly triple the velocity reaching the rotor while letting the moving parts sit at ground level, where they are cheap to reach and maintain. Putting the generator on the ground removes the tall, heavy nacelle that forces a conventional turbine onto a massive tower, and the small enclosed rotor poses little hazard to birds. The design drew sharp skepticism from wind engineers, who argued the energy lost pushing air through the ductwork offsets much of the speed gain, and it has not reached commercial deployment. It remains the clearest attempt to solve wind generation by moving the wind to the machine rather than the machine to the wind.